Hope that's okay.
So first, yeah. Right, so to start, what is quantum cryptography? So well, it is cryptography in a world that has to reckon with quantum information. So now on the theoretical side, there are actually a few research directions that fall under the umbrella of quantum cryptography. So first, possibly the most natural question to ask is, are our classical cryptographic protocols still secure if an adversary has access to a quantum computer? And as we all know, Shor's algorithm can efficiently factor numbers. And this will allow us to break most of the cryptographic schemes that are used in practice today. So it's natural to study ways in which we can sort of classically upgrade our protocols, but also as well as upgrade our security proofs so that they're quantum safe. And I want to stress that proving security against quantum adversaries is not actually as simple as just replacing a quantumly broken hardness assumption with one that is quantum secure. In fact, as we heard from Mark Gendry in the Simons Colloquium a few weeks back, there are actually quite a few subtleties that arise in improving security in the quantum setting, but I won't get into this here. And the second very exciting research direction is to design protocols that actually actively use quantum information, quantum communication, with the goal of realizing primitives that are even impossible to realize classically, or to realize them under weaker assumptions. And finally, I would say that there is a third sort of broad research direction, which tries to answer the following question, which is, how can we as classical beings certify that some alleged quantum device is indeed quantum? And even better than that, how can we certify that the device is performing a specific quantum computation or generating true randomness, for example? And there are different lines of work here that achieve such certification procedures in various models and under various assumptions. And now in this tutorial, I'll focus on the second research direction. This is what Anne will also be talking about. And I find this research direction the most exciting, partly because we are really still scratching the surface here, I would say. So what is it that makes quantum information so special for realizing cryptographic primitives? Well, it's mainly two ingredients. So the first, probably the most important one, is the no-cloning theorem. The second is entanglement. So in the rest of this tutorial, I'll show you basic ideas for how to use these two ingredients. So first of all, what does the no-cloning theorem say? Well, classically, it is always possible to copy any string of bits. And this is essentially because one can just read the string without disturbing it. But as you all know, quantumly, this is not possible in general. And now, sort of from the point of view of storing quantum information, this represents a fundamental challenge because it basically says that quantum information just cannot be backed up. However, from the point of view of cryptographic protocols, this represents an exciting opportunity because it fundamentally restricts the possible strategies of an adversary. So in particular, an adversary cannot simply copy quantum information. So let's see a simple example of the no-cloning theorem in action. So I'll describe a quantum money scheme, which dates back to the 1970s. So early on, and this scheme is by Wisner. And the idea of a quantum money scheme is to leverage the no-cloning theorem to create banknotes that are impossible to counterfeit. So where the inability of an adversary to counterfeit banknotes is guaranteed by the laws of physics. So in a quantum money scheme, basically a banknote will be a quantum state. And here's how Wisner's scheme works. So there is a bank that generates quantum banknotes, which are handed to parties like Alice. Now, a banknote consists of a number of qubits in this scheme, where each qubit is one of four possible states, 0, 1, plus, or minus. So or more precisely, let n be the number of qubits in a banknote. Then the generation procedure is the following. The bank samples a uniformly random string of basis choices theta, computational or Hadamard for each bit, as well as a uniformly random string x of the same length. And the bank then sort of encodes the string x in the basis theta, meaning that for the ith qubit, the bank looks at the ith bit of theta And this determines the basis choice, computational or Hadamard. And then the ith bit of X determines whether the qubit is 0 or 1 for the computational basis, and plus or minus for the Hadamard basis. So for example, here the fourth bit of theta is H, so the fourth qubit is in the Hadamard basis, and the fourth bit of X is a 1. And so this qubit here will be a minus. Now the bank saves this information, the theta and the X, for each banknote in some database, and it also assigns this information some classical serial number so that it can go and retrieve it later on. And now to spend or to redeem rather a banknote, the user Alice simply returns the banknote to the bank with the serial number, and the bank just looks up in their database for the theta and X, and it then measures the banknote in the theta basis and just checks that it obtains outcome X. If so, it accepts, otherwise it rejects the banknote. And so you can see that if Alice honestly returns the banknote that she receives, then the verification procedure will of course pass. But what we're interested, or what is more interesting, is security. So how is security defined? Well, informally, we want to say that it is not possible for an adversary who receives one valid banknote to produce two copies of it, which are both sort of simultaneously accepted by the bank. In particular, we want that this should happen at most with, say, exponentially small probability in n. So in other words, the banknote cannot be redeemed or spent twice, except with this very small probability. And so what is the intuition for security here? Well, the intuition is that measuring a qubit in one basis to learn a bit of X, this sort of destroys the information about X in the other basis, right? So it should be hard to recover more than, say, a constant fraction of the bits of X. And notice that so far, the security of the scheme is information theoretic. So what I mean by this is that the scheme, at least intuitively, should be secure even with respect to a computationally unbounded adversary. So it doesn't matter how much computational power an adversary has. The security seems to be essentially a consequence of the uncertainty principle, which is basically a strengthening of the Necronic Theorem. So I'll move on to another example, and I will try to say a little bit more about what goes into formalizing the intuition for security here. So the next example is the famous BB84 protocol for key distribution. I'm sure many of you will have seen this. So after describing the protocol, I will try to highlight some of the ideas that go into a bit more formally proving security. So first of all, even before proving, even before any sort of quantum information is involved, what is a protocol for key distribution? Well, this is an interaction between two parties, Alice and Bob, at the end of which the two parties ideally possess the same key, K. And this interaction, this communication happens in the clear, so over public communication channels. So it's meant to be entirely visible to an adversary Eve. And now the security guarantee that we want is that this key should look uniformly random to any adversary Eve that eavesdrops on the protocol, meaning Eve has access to any communication between Alice and Bob, yet she should have almost no information about the final shared key K of Alice and Bob. And now, why do we care about a key distribution protocol? Well, once a shared secret key is established between Alice and Bob, they can use it to communicate in an information theoretically secure way. So now, classically, designing a protocol for key distribution that is information theoretically secure is impossible. And this is because an adversary sees exactly, if you see here, an adversary sees exactly the same things that Bob sees. There is no asymmetry at all between Bob and the adversary. So if Bob is supposed to learn a key, then so can the adversary. And sort of tacitly at the core of this observation is this implicit fact that the adversary can always trivially copy the classical communication, and it can do so without Alice and Bob noticing anything at all. So quantumly, things are much more interesting. So the crucial difference is that if we allow for quantum communication, then it is actually not possible for an adversary to just trivially copy the quantum communication. So in a quantum world, the hope is that basically any meaningful attempt that the adversary makes at extracting information will result in a disturbance of some kind that can be detected by Alice and Bob. And the BB84 protocol realizes precisely this intuition. So the protocol is the following. So Alice will start by sampling uniformly random theta and x of the same length n, where theta denotes sort of n basis choices. She then creates n qubits, similarly to the Wissner's quantum money scheme. So for the ith qubit, the ith bit of theta specifies the basis again, and the ith bit of x says whether you have 0 or 1, or plus or minus. And now Bob, who receives the n qubits, samples a uniformly random theta prime and measures in the basis specified by theta prime. And let's call x prime the outcome of all of these measurements. Now, the next step for Alice and Bob is to perform a consistency check. So the purpose of this is precisely for them to be able to identify if an eavesdropper has tampered with the quantum states that Alice sent to Bob. So as part of this consistency check, Alice and Bob first exchange publicly their theta and theta prime. And then they check that whenever they measured in the same basis, they also got the same outcomes. So more precisely, Alice and Bob, they first identify the locations, the indices where they measured in the same basis. Then Alice picks a uniformly random subset of this. And for this subset of locations, Alice and Bob communicate their outcomes to each other in the clear. And they verify that the outcomes are the same, that they're consistent. So this whole process here is what we can call sort of a consistency check. In the literature, it's also referred to as parameter estimation. And now, if this check fails, Alice and Bob abort. If it passes, they proceed forward. Okay. And so how do Alice and Bob get a shared key in the end? Well, Alice and Bob simply take the measurement outcomes from the remaining measurements where their bases agreed, which were not already used in the consistency check. And let's call these outcomes x tilde and x tilde prime for Alice and Bob. And we refer to these as the raw keys. So if the adversary didn't tamper at all with the protocol, then x tilde and x tilde prime are exactly equal. But if the adversary has tampered with the protocol, then it's possible that the two raw keys differ slightly, or that the adversary has some small amount of information about them. And so basically, as the final step in the protocol, Alice and Bob go through an entirely classical procedure that allows them to obtain keys that are a little bit shorter, but identical, and such that they look uniformly random to an adversary. So this is the final step of the protocol. I won't go into the details of this last step, since it's an entirely classical procedure. It's also quite intuitive, actually. And so in the last few minutes, I just want to highlight some ideas that are involved in formalizing the security of the BB84 protocol. And of course, these are also relevant to the security of the quantum money scheme. So, so far, I mentioned entanglement at the beginning, but it has not made an appearance yet. So we've only talked about no cloning. In fact, it does not seem like entanglement is involved at all in the BB84 protocol. However, I will show you now that we can actually recast the BB84 protocol in a way which is equivalent and in which the role of entanglement becomes more apparent. So consider the following protocol. Alice starts by creating n EPR pairs, so n pairs of maximally entangled qubits, and she then sends n halves of these EPR pairs to Bob. And so here I'm using the same color to denote entanglement. And now Bob, just like before, picks a uniformly random basis theta prime and measures the qubits that he received according to theta prime. And again, let x prime be the outcome. And now only after this has happened, Alice picks a uniformly random basis theta and measures according to theta, and let X be the outcome. So the rest of the protocol is exactly the same as before. Alice and Bob run a consistency check, they get their respective raw keys, and then finally they extract a shared key. But now the point is that Alice and Bob's actions, 1 and 2, they commute, since they act on different qubits. So the protocol here is actually equivalent to one in which Alice immediately picks a theta and measures, and only after this sends over the half EPR pairs. But notice that the latter protocol, where Alice first measures, is actually identical to the original BB84 protocol, because once Alice measures her half EPR pairs in the theta basis and gets outcome X, Bob's half EPR pairs, they collapse precisely to the right state. So which is the string X encoded in the theta basis. And so recasting the protocol sort of through the lens of entanglement is actually quite helpful for proving security. So let's talk briefly about security. So for security, recall that an adversary, Eve, has access to all the communication between Alice and Bob. In particular, Eve can intercept the qubits on their way from Alice to Bob. She can then apply any arbitrary quantum channel to these qubits, and then she can send n qubits in some possibly different state to Bob, and she will keep some information for herself. And now, as a consequence of this, Bob and Eve's information could be entangled as well. Now, the first observation that I sort of want to point out is that if Eve's attack, so if the quantum channel that Eve applies, if it leaves the qubits received by Bob still maximally entangled with Alice's qubits, then there is a fact about maximally entangled states that guarantees security. So this fact is called monogamy of entanglement. And it says that if Alice and Bob are maximally entangled, then their state must be in product with Eve's, in which case Eve will have no information at all about Alice and Bob's key. So one possible strategy to prove security here is to argue that the only way for Alice and Bob to pass the consistency check is for them to be sort of close to maximally entangled. And here for this, it's crucial that Alice is choosing theta uniformly at random after Eve's channel has been applied. And so the last thing that I want to mention is there's sort of another approach, which is a little bit more direct for proving security, which is to leverage and prove a formal tool, which is called an entropic uncertainty relation. And so now we're back in the same scenario where Eve has intercepted Alice's quantum message. She applies a quantum channel and she sends n qubits to Bob. Now, after this, theta is revealed by Alice as part of the consistency check. And now an entropic uncertainty relation is something that looks like the following inequality, where here K is the typical length of the row keys, the expected length of the row keys. And now, without getting into the details of what these entropies mean exactly, this relation just formalizes the intuition that no matter what adversary, no matter what sort of adversarial channel Eve applies, there is a trade-off between the uncertainty that Eve has about guessing Alice's measurement outcomes and the uncertainty that Bob has about Alice's measurement outcomes. So in other words, this formalizes the intuition that in order for Eve to obtain information about Alice's raw key, she has to, in some sense, destroy some of this information for Bob. So here, the first term represents roughly the number of bits of uncertainty that Eve has about Alice's measurement outcomes, given her own subsystem, so whatever she kept for herself, as well as theta. And the second term, in a way, sort of quantifies the uncertainty that Bob has about Alice's raw key, given, again, all of this information. And so a typical security proof would first upper bound the second term, conditioned on the consistency check having passed. And then as a consequence, this would imply that the first term must be large, meaning Eve has a lot of uncertainty about the raw key, which is what we want. So this is all that I wanted to talk about in this intro. Thank you for listening. I will now go ahead and introduce Anne. So Anne Broadbent is a professor in mathematics and statistics at the University of Ottawa. She is the recipient of the 2016 Eisenstadt Prize. She obtained her PhD from the University of Montreal and was a postdoc at CIQC before moving to Ottawa, and has actually many influential contributions throughout quantum cryptography. She has worked extensively on delegation of quantum computations. With co-authors, she proposed the concept of blind quantum computation. She has also worked on zero-knowledge proofs in the quantum setting, more recently on a variety of unclonable primitives. And I have to say personally that in the few years that I've worked on quantum cryptography, I found that Anne often sets trends for other people in the field to follow. So I'm very much looking forward to your talk. So I'll stop sharing my screen. You can go ahead.
Thanks a lot for the lovely intro, not just the presentation, which was really good to get us started on this topic. Thanks a lot to the entire team for the invitation today and to the audience for being here today. Okay, let me get my windows set up. Great, so we're going to talk about, no surprises, we're going to talk about quantum unclonability. Starting point is the no cloning theorem that we've heard about. And then, okay, so what does this mean? So there's no cloning theorem, of course. So for me, this means that a useful analogy for quantum information, it's much more like a physical object. It's much more like an apple. It's possible for somebody to taste an apple, but that's going to leave a trace on the apple. It'll be noticeable. It's possible for me to share my apple with a friend, but we only have one apple total. I can take half, the other friend can take another fraction, but there's only one. So you can actually take that analogy pretty far and kind of imagine that quantum information, it should really have these physical properties that we're used to in the everyday objects. So in the studies of cryptography, you can try to look for those properties of everyday objects and try to emulate those using quantum information. Okay, that's the big story, the big lines of the story. So we want to discuss what is this unclonability exactly? I don't think we have a really good answer to that, but we're trying to find embodiments of unclonability at least, and maybe that's gonna lead us to a better understanding of what it is unclonability. These are not new ideas. Actually, in a very kind of early paper in 2009. Aronson already suggested the idea of quantum copy protection for software, and it's linked to quantum money. And then in a nice, you can hear lots of ideas in a nice after dinner speech that he gave about 5 years ago. And it's kind of interesting to look back to see how much progress we've made in those 5 years. I'd like to bring up a comparison with a related area of research, which has maybe at least 20, maybe 30 or 40 years of leeway. So the study of cryptography, and I'm talking about modern cryptography, started about the 1980s when we started to get public key cryptography. We started to get a really good handle on security definitions. And that's where we understood, what does security mean? And the short answer that came in this probabilistic encryption, semantic security, et cetera, is that security for an encryption scheme can be defined in terms of a game. There are many different games, depends really what type of security you're looking for, but I think that's the conclusion. So maybe in the study of unclonability, it's these games that are important to look at, and we're going to be talking a lot about games winning probabilities for games and how that it can embody unclonability. Why should you care? Okay, I acknowledge that this is a multidisciplinary audience, and there could be many reasons for different to care about these coming from different aspects. So this talk is about the software side of unclonability, what we could achieve on paper, in theory, what we can prove, what we can define, and then the challenge is to look at the physical systems and to see how we can map those our pipe dreams into the actual physical systems. So that's one direction that's really interesting. And then I hope that it can also go in the other direction, that the systems that we're building, we can ask, well, what software would you want to run on these, and how can that influence the devices that we're building? Yeah, so it goes both ways, hopefully, and that's why I hope that you'll be interested. Okay, so, oh yes, and please feel free to ask questions. Maybe Andrea, you can interrupt if there are clarifying questions that really help to understand, but the deeper discussions we can keep for the final discussion. Okay, so we had a nice introduction on quantum money. What's quantum money? It's actually, in Wiesner's language, he actually had proposed subway tokens. And I think that's a nice analogy. It's really like a token of authenticity, something that can be verified at the subway station where you insert your token to prove that you've paid for that token and that nobody else can copy that token, so you can't, sell counterfeit subway tokens. And that's a nice analogy. It's about being able to verify the origin of the encoding, and that's it. So I just want to bring up some recent work, actually a bit of a revival in 2012. All sorts of new things came out of these ideas that were really the precursors of quantum cryptography. They were really early ideas. So one thing that came out was noise tolerant quantum money. So this is also going to be a theme in my presentation, talking about, well, we have these theoretical protocols. Wiesner's quantum money, it's actually kind of useless because it would any error would make the bank reject, and that would include noise from the storage or from the measurement. So noise tolerance is important and feasible with current technology. Well, that became a possibility in 2012. Also quantum money with classical verification, and also this totally new class of quantum money that's called public key money, quantum money. Another way to see it is publicly verifiable quantum money, meaning that anybody can verify it. So it's much more useful in a distributed environment where you might want to spend your money at different locations and not just cash it in at the bank. So some pretty powerful techniques were developed in that area. An open question that remains, as far as I know, is to make these public key quantum money schemes relevant for current technology. So like NISC era, what because right now they use pretty profound encodings and cryptographic techniques. So as far as I know, they would need to be adapted and looked at in detail to see if we can do these with current technology. So I would like to present unclonability in a type of hierarchy in terms of the information that it encodes. Quantum money, it's just the token. There's actually no information encoded. What can you do with it? You can verify it, that's it. But what about information? Could we have a way to encode information to make that information unclonable? Meaning that there's simultaneously a message and a method to somehow verify or prevent cloning or something related to unclonability on that message. So that, I kind of call that in a category of unclonable information. So you automatically might think of encryption schemes. So encryption is a way to take a message, convert it to something, and namely it's not readable by an adversary without access to the key. Similarly, we can think about encryption schemes that will take a classical message, convert it to a quantum ciphertext, and then try to look for some unclonability properties there. I'll have two examples. The first one I want to go through is called certified deletion. And there's once more a physical analogy to certified deletion. Imagine Alice wants to encrypt a message. In order to encrypt it, she inserts a message into a safe, and closes the safe. And she sends that to Bob. Bob, at this time, he has a choice. He could return the safe to Alice. If he returns the safe to Alice unopened, then Alice will actually know that Bob never read the message. Or, actually this is an exclusive or, he can do this first option, XOR the other one. He could decide to keep the safe. And then we'll say that at some point the key becomes available, namely the combination. This could either be by design, eventually Alice might reveal the key, or maybe this is using public encryption and eventually some computational assumption is broken. So eventually the key is revealed to Bob. When he gets the key, he can open and read the contents. But the point is that if he's returned the safe to Alice, then Alice knows that he won't be able to read because that was before the key was leaked. However, if he keeps the safe, he can read it. And the question is, can we achieve this in a digital world? Digital meaning a conventional or classical encoding. The answer is obvious no. So pretty clear, proof by contradiction. If the encoding here is a classical message, it's a digital bit string, it can be copied. Bob on his side can make 2 copies of the encoding. It's a proof by contradiction. So assume that we do have such a certified deletion scheme. With the first copy, he can convince Alice that he deleted it. And the second copy, he can keep that and then decrypt in the future when the key K is revealed. So clearly, proving deletion is not possible in this context, at least classically. Of course, since I bring this up, there's a way to do this with quantum encodings. So the quantum mechanics, like once more, bringing back the analogy of the apple, it's like the best of both worlds. You get a digital type of encoding where you can reason about physical systems that encode the information, etc. But you get the properties of the physical objects being unclonable. Unclonability here is that Bob can't make the 2 copies of the ciphertext in order to obviously break the system. So we're going to encode a classical message into a quantum state, and then Bob will be able to prove that he deleted a message, and the proof will be a classical string. So that's even better. He's not actually returning the apple. He's like, I don't know, measuring the apple and returning the result of the measurement, and that convinces that the apple is destroyed. Here is a simple scheme. I just chose 4 qubits. It uses the same notation as Andrea, so that's very fortunate for the Wiesner encoding. It's also in the BB84 key distribution encoding. We have this random basis theta, a bit string R. Oh, he may have called this X. And the Wiesner encoding will be these 4 qubits, based on the basis. If theta is 0, then it's a computational basis encoding. If theta is 1, it's a diagonal basis encoding of the bit in that position for R. And then there are 2 substrings. RComp is the substring of R where the bits were encoded in the computational basis, and RDiag is a substring of R where the bits are encoded in the diagonal basis. To encrypt, we're going to use RComp. So we're going to use the one-time pad of the message with this substring RComp. The deletion will be using the qubits that are encoded in the complementary basis. So to delete a message, to produce a proof of deletion, Bob would measure all the qubits in the diagonal basis. And that's going to give him a bit string Y. If he's honest, everything's been honest so far, there are going to be some wildcards, and these are these stars. They will be actually uniform in the honest case. That's because those qubits were encoded in the computational basis. And this bit 1 and 0, they come from this RDiag, and they're fixed because he's measured in the diagonal basis and the encoding was diagonal. To verify the deletion, all Alice has to do is to verify these RDiag positions that they're consistent with this 1 and 0 for this, in this case. And decryption, remember, decryption is complementary. So, Bob should either prove deletion or wait till he gets the key and then decrypt. If he wants to decrypt, he gets the key theta, and he uses that to measure the qubits that are in the computational basis. Then he gets RComp, and then he can undo that one-time pad, and then he'll be able to compute the message M. That's the basic scheme. And the proof intuition really follows closely what Andrea was telling us about the proof of BB84 quantum key distribution. Actually, there's a way to massage the problem of certified deletion to make it look really, really close to key distribution. So then we can have access to all those proof techniques that are quite developed. So the idea is that the probability of predicting this R-diag substring, if Bob wants to be good at convincing Alice that he's deleted, he necessarily needs to become bad at predicting R-comp, and R-comp is what's required in order to be able to decrypt, even given the key. So these are these kinds of uncertainty relations. Here, C is the overlap between the measurements. It's 1/√2 in this case. Okay, I talked about security definitions, games. Here's what it looks like for certified deletion. There are simultaneous goals going on here. There's the encryption scheme. So we need to have correctness for the encryption scheme. It's actually not written here, but obviously Bob should be able to decrypt. And then there's but he should not be able to decrypt if he has convinced Alice that he has deleted. So that's a long sentence. So imagine trying to formalize that mathematically. This is what this is doing. Okay, so Bob chooses a message. And then Alice chooses a key and a bit B, randomly a bit. If she decided to choose B = 0, she's going to set a message to be a constant message. It could be anything. Let's choose 0. If B is equal to 1, she'll set the message to be the actual message that Bob chose. And then she will encrypt that M, either 0 or the message, depending on the bit B. So now it's all about Bob being able to tell whether she had encrypted the message 0 or the message that he chose. This comes up in semantic security and distinguishability in conventional cryptography. So, but don't forget that we have this deletion. So Bob produces a proof of deletion, a candidate proof of deletion, string Y. He can do any type of process to come up with that. And then Alice may accept or not. She will base her acceptance on whether or not this R-diag is satisfied. Okay, and then the key is revealed. Bob gets theta, then he can do any operation and produces a bit B prime. In order to win the game, he has to produce a bit B prime that's equal to B. So he has to have been able to tell between an encryption of 0 and an encryption of 1. And Alice should have accepted the proof of deletion. So we want that probability to be low because we want to have that once Alice accepts the proof of deletion, Bob should not be able to decrypt. And this condition here is related to being able to decrypt. So the best we could hope for is that this probability would be 1/2, and that's if Bob guessed randomly, uniformly at random, and we'll add a little fudge factor, and this is what we're going to ask for. The proof outline, I really feel like I can go over this quickly because it's very similar to what Andrea said, that we will look at instead at this entanglement-based game and use entropic uncertainty relations to bound the probability that Bob is able to decrypt given that Alice accepted the proof of deletion. And I gave you the basic idea. We can use a privacy amplification, namely a universal hash function, to amplify so that we can get really this negligible here. And also, since we were able to use all the techniques of quantum key distribution, we were able to make this noise tolerant. Therefore, it has all this nice properties, finite key analysis also that we already have for QKD, which makes QKD so practical today. And there's some follow-up work that has looked at the composability and device independence of certified deletion. Okay, so that was one encryption scheme that has this unclonable property. There's another one I want to tell you about maybe a bit more quickly because it's actually not as mature. It's a nice idea. There's still lots of open questions on unclonable encryption. If encryption is classical, it's obvious that an adversary can make copies of the ciphertext and then do whatever they want with that ciphertext. Namely, if the key is eventually revealed, no, same thing, either by design or eventually because some assumption is broken, then both of these parties could decrypt. With the no cloning theorem, this basic attack doesn't happen. So that opens up the possibility of unclonable encryption. This is a security game that embodies this. So suppose that here the message is chosen uniformly at random. There's some pirate or attacker here that tries to tries to copy the ciphertext, basically, excuse me, and then the key is revealed. And then we look at these messages here that these adversaries output, and M1 and M2, and the probability that all of these would be equal, M1 is equal to M2 is equal to M, well, they could give a coordinated guess, and since the message is originally uniform, that probability would be 1/2 to the n. So we could hope for this type of optimal security in case of a quantum encoding. We actually don't know how to achieve this, but we've done something relatively close with a graduate student, Sebastien Lord, and we were able to bound this probability with a factor of 9 here, and also in the quantum random oracle model. So frequent technique in cryptography, if you can't prove something, add an assumption. And the quantum random oracle model is an assumption that gives you a handle on what the adversaries are doing and kind of forces them to have a specific behavior. And that's really, that behavior is really, it turns out to be really useful in proofs. So the quantum random oracle model is actually an idealized version of a hash function. And in this case, it really helped us to nail down this proof. The idea of the scheme is very close to certified deletion. You'll take the message, XOR it with a random bit string, and then encode that random bit string in a random basis. These Wiesner, what's more, these Wiesner states, they're hard to clone, actually not clonable. And so that gives us the limitation on the clonability of the ciphertext, even given the key. This question of how well Bob and Charlie can simultaneously guess M is equivalent to the entanglement-based question, where this pre-shared entangled state arrives, row ABC, and then Alice is going to measure on a random basis, the same game that Andrea described. Bob and Charlie are going to get the key. It's actually not exactly the same game because we actually don't have control over what Bob here is doing. This game is called the monogamy of entanglement game, and it models the security that's required in one-sided device independent QKD. And that's exactly what we need to do, exactly the same model we needed for unclonable encryption. So we're able to use this bound. And this bound here comes from this paper, and basically amplify it using the QROM, as I mentioned, was an extra assumption. Unclonable encryption, it's an area where there's lots of open questions. We could try to get rid of the QROM. We could try to improve the security definition. So this random message M and trying to match it precisely, it's actually quite weak. So we should try to look for more of an indistinguishability-based security definition and try to achieve that. That's what this is summarizing. And then there's, okay, related to that, there's an even simpler problem that, as far as I know, we don't know how to solve. And it's relatively easy to explain, so let me give it a shot. Here we have only a single bit that we want to encrypt. So we're looking for an encoding scheme. It encrypts a bit. Same thing as before. Some pirate tries to split it. Bob and Charlie get the key. And we would like to have the probability that Bob and Charlie are both able to predict B should go to 1/2 as n gets big. And that's all. And as far as I know, we don't know how to do that. So it's a nice open question. Okay, so moving on in the hierarchy. I told you about unclonable tokens, unclonable information. There's another level in the hierarchy, which is functionality. Okay, so yeah, in your everyday computing, you store your data, that's data, but then you also have computer programs. You have software, also sometimes represented as circuits. So could we represent functionality, function, circuit, software, and make that unclonable using a quantum encoding? So that's this next level that I want to tell you about. Sometimes it's called copy protected software, introduced by Aronson. Okay, so what is quantum copy protection? It gets trickier. It gets trickier as you go up in the levels of this hierarchy. Okay, so we have a function. We want to somehow encode it into some quantum storage and quantum system. And then we'll want to be able to run that software. So we'll have this quantum computer, kind of like an interpreter, and we'll give it an input X, a classical input, and we want that the computer would have a way to compute f of X. F was encoded originally here, right? So it's a classical description of a piece of software. And so this computer doesn't have F, except it has it via this quantum disk, right? So that's the functionality that you should be able to achieve. What about security? Suppose a pirate gets a hold of the piece of software and tries to make pirated copies, right? That's what pirates do, right? So then he maybe sells those copies to Alice and Bob. But we want to prevent this pirate from doing anything useful. Namely that these pirated copies should not be good at simultaneously allowing Alice and Bob to evaluate the function. How we define that exactly is coming up. It's kind of tricky. Okay, so the first observation to get you thinking about the quantum software is that quantum software is actually reusable up to a certain point. So we're not trying to limit reusability. I'll tell you how it's reusable. So if you had a quantum software, a computer, interpreter, and it's able to compute F, okay, never mind this P here. Then if it's correct, then that F is actually a classical bit string, and you can copy that classical bit string. And then we could undo that computation. So without loss of generality, this computer is doing a unitary. And so for this computer, see it's backwards, it's running the unitary in the other direction. And by these lemmas, all called almost as good as new or gentle measurement, this has actually reconstructed the original software program up to some small error. So this shows that we're able to evaluate the function and not lose the original quantum program. So the software is reusable. Okay, so what am I talking about? I'm not talking about preventing reusability. I'm talking about preventing simultaneous uses. That's copying. Copying means I can use it and Andrea can use it at the same time. What types of families could we hope to copy protect? So it would not be possible to copy protect learnable functions. These are functions that by learning a polynomial number of points, then we can actually reconstruct the function, and that would be an attack. You don't even have to look at the quantum thing, you just need to evaluate it as a black box. So that means these functions cannot be copy protected. The other observation is that if we have perfect correctness in the scheme, then we could not have security against unbounded adversaries, because an unbounded adversary could do this attack in the previous, this reusability attack in the previous slide and reconstruct the entire truth table, and that would be a copy. That would kind of consist in a copy of the software. Okay, so that's just to get some bearings on this domain. In order to simplify the situation, because it's already rather complex, we're going to limit to point functions. Limit ourselves to copy protection of point functions. Point functions are a very simple class of functions. They are not learnable, so there's hope that maybe we can copy protect them. You can see these as password verification functions. There's a single point P that accepts, and all the other points will reject. And the important piece of information about the function is P, and that's the point that accepts. Okay, I'm not going to go into details about this little footnote. Okay, now maybe we could talk a little bit more about what is copy protection, at least for point functions. We want correctness. So given the software should be able to evaluate the function, this point function here. And now we'll talk about a distribution. this distribution has the property that with half probability, the input will actually be P. And then all the other points are chosen with uniform probability over the other points. So the definition that we're going to be able to achieve is average correctness. And that means that up to some error term, the outcome is correct in expectation over the choice of X, where X is sampled according to this probability distribution. There's a stronger notion of correctness, which would be worst case correctness. Security. We're going to follow this definition from Andrea and co-authors. You can imagine, okay, so yeah, the challenge is that what does it mean? I kind of like this exercise. What does it mean to have a functionality? Like, you need to answer that question in order to be able to understand what it means to not have a functionality. And that's the security that we're looking for. You know, we're trying to show that it's not possible for Alice and Bob to both have the functionality. So what it means to have a functionality, well, one operational way to look at that is that it means that the user can evaluate the function. So if there's a referee asking questions, okay, please evaluate the function at this point, gets the answer, verifies, etc., then the referee can become convinced that that user has the functionality. Similarly, if the user does not have the functionality, then getting these challenges and answers, there should be lots of errors in those answers. Okay, so there's this referee, and it is giving challenges to Alice and Bob separately. Alice should answer what's FP, or P is unknown. And the referee knows P, Alice doesn't know P. So she gets input X and she should answer that. And Bob gets input X2. Oh, she gets X1, he gets X2. And the challenge distribution is also sampled from the one that we talked about previously, namely with half probability, the xi is the actual point P. And then with complementary probability, all the other choices are chosen uniformly. So we'll say that Alice and Bob win if they both output correctly. So they're both able to predict the outcome of that function, that point function. And note that there's a trivial strategy here where they would win with probability half, namely they would give a coordinated guess, a uniformly chosen coordinated guess. And so we could hope for the security, which would be a half plus epsilon, a little security loss. We could hope for this quantumly. Classically, of course, we could not hope for that. It would be 1. They could always win by copying. Okay, so quantum copy protection, when it originally came out, you know, as I said, if you're having trouble, you can add an assumption. So quantum oracle is an assumption, and it was shown that we could do quantum copy protection relative to this quantum oracle. That was improved to a classical oracle recently, and then that was transformed to a quantum random oracle, which is an upgrade because in the result, because the quantum random oracle does not depend on the function that you're trying to evaluate. So that's important to be able to to do that. And so this demonstrated that you know we can do these. Well, it was limited now to point functions, but we can do it using a QROM. And the work I want to tell you a little bit more in detail today is no assumptions, but the class of adversaries are called honest malicious. So that means that this first evaluator is going to be running the honest evaluation procedure, and the second one can be arbitrarily malicious. I also want to tell you about secure software leasing, which is a related primitive, and it's been kind of in the last year, there's been a lot of results. And basically, it's that Alice wants to encode a piece of software and give it to Bob in a way that Bob has a way to convince Alice that he's returned the software. So maybe she leases it for 1 week. After a week, Bob is supposed to return it, and then she can verify that it's been returned, which means that Bob cannot evaluate that software anymore. But he could keep some side information, but basically that should be useless for him in order to evaluate the function. It turns out that there's a link between secure software leasing and the honest malicious copy protection that we've seen in the previous slide here. So it's just a way you just need to turn your head in a different way, and they're actually the same thing. So Alice, this blue thing would be the piece of software that Alice creates. The pirate trying to return it here, well, one way of verifying a return is to run the honest evaluation and to check that it works. And so that's why these two things are purple. And this green thing is the side information that the pirate keeps and tries to use that to his advantage. And then we've showed, actually, they're not equal. I apologize. The arrow goes in this direction. So if you're able to show honest malicious copy protection, that implies secure software leasing. So that's the link between these things. And there's here's some recent work on secure software leasing. First of all, I should point out that secure software leasing is impossible in general. So there's a family of functions that cannot be turn into secure software leasing programs. And this is also related to the recent result on the impossibility of virtual black box obfuscation in the quantum world. And this paper simultaneously has an impossibility and possibility. So a way to do SSL for point functions, assuming a bunch of things. Those assumptions were relaxed in this recent work. And then in a different model where the evaluation does not need to be honest, this work by Andrea and co-authors that I've already mentioned also shows how to do SSL, as well as this recent work that I want to tell you a little bit more in details today. The way that we're able to do this honest malicious copy protection is via some other quantum cryptography primitive called quantum total authentication. Okay, so this arrow I've already talked about, and now I want to focus a little bit on how we do this. And the interest is that it links another quantum crypto primitive to copy protection. Quantum message authentication, it's a way to verify the authenticity of a message. So if there's a pirate that interferes with the quantum message, then Bob should be able to detect that. That's the property of message authentication. And then there's this other class, which is an upgrade. It's called quantum total authentication, and it has this extra really nice property that conditioned on acceptance. So if Bob accepts, we can actually say that the pirate here, the system that the pirate keeps, has nothing to do with the message or with the key. So it's almost a little bit like quantum key distribution, kind of saying that when Bob becomes convinced here, we've kind of squeezed out Eve, and Eve has no information. So that's what we're going to use as the security property to be able to show quantum copy protection. And yeah, for the experts that are here, we're going to map the point P that we're trying to encode in as the point function. That P is going to become the key of the authentication scheme. So we're going to have this authentication with a subscript P, and the verification will also be using the same P. On a fixed state psi, which is the dummy state, it could be anything. So we're going to use the properties of the authentication scheme in terms of how it acts on how the keys kind of relate to it. So namely, in order to encode the point function f sub p, we'll authenticate a arbitrary state using as key the point. And then the evaluation should be clear. You know, if you're verifying with the correct key, then the output will be 1, and there's been no tampering. If you're verifying with the wrong key, well, actually, we had to work on that a little bit, and that's why we only get average correctness. If you verify the wrong key with high probability, you'll output 0. And the security, we're going to use the properties of the total authentication scheme to be able to argue that if Alice is accepting on the correct key, then Bob's remaining state is independent of the message and of the point. So that means that he should be bad at winning this game, which of the challenges, because basically he'll output the same thing no matter if the challenge is the actual point or a different point. Okay, so I wanted to talk about some open problems in quantum copy protection. Right now, for the result that I was telling you about, we only have this average case correctness, so we could try to get the standard correctness. And we could try to get security against 2 malicious evaluators. Right now, it's honest malicious. I think this is a limitation on the proof techniques that we're able to come up with. I don't think it's actually a fundamental limitation. We could go beyond point functions, actually beyond compute and compare. I kind of skipped over this, but the point functions imply this functionality for a slightly larger class. So we could try to go beyond that slightly larger class. And then also in this theme of trying to make things realizable. So looking at these schemes and trying to make them prepare and measure, trying to make them fault tolerant so that they could be implemented shortly. Great, so I wanted to leave you with a really kind of like a dream, which would be maybe the next level. I'm not sure if this is the next level or maybe slightly something different, like on a parallel track. Unclonable proofs. This was actually brought up by Aronson about 5 years ago. And the question is, okay, proofs. A proof is something that can be verified. So a proof of NP language, QMA, QCMA, maybe something else. And the question is, can we make these proofs unclonable, or maybe are they already unclonable, or what are the consequences of them being clonable or not? So a pirate gets a proof, like yeah, an assignment to 3-sat instance, or maybe a QMA proof, and then he tries to create these pirated proofs. And then the question is, can we limit the possibility that both Alice and Bob could simultaneously become convinced of the validity of that proof? And how do you even define that? And like, what does that mean? I think there's lots of things to look at here. So we've only really scratched the surface. If I can kind of go out on a limb and say, well, when we finally understood zero knowledge proofs about I think it was close to 40 years ago, 30 to 40 years ago, that really kind of opened up an entire area. We understood this, the simulation paradigm, what it means to learn nothing, and it had repercussions on, huge repercussions on cryptography and also on complexity theory. So maybe these unclonable proofs will also really give us some good insight on unclonability. So with that, I would like to thank you.
Thank you, Anne, for a very enjoyable. Thank you for a great talk. So I think now we will open the floor to questions.
There's also questions that you were mandated to ask, but I'll let you.
Oh yeah, I mean, I guess I can ask a meta question there. So there's a bunch of questions that have sort of been asked at every seminar, or a subset of those questions. But okay, so I guess I can start us off with one question along those lines, kind of rephrased for the context of this talk. Sorry. So I guess I was wondering, what are your thoughts on whether it's worthwhile, since we have a lot of people working on experiments in the audience, whether it's worthwhile, since many of these applications rely on quantum memory, whether it's worthwhile to experimentally build quantum memory or focus on that line of research, and what are your thoughts on feasibility? Yeah, I guess this is also to stimulate the discussion.
Yeah, I think the memory hasn't had as much focus as it should. So in a computing system, in a network system, I really see that there's the communication that's important. There's the computation that's important, and we hear a lot about those, both quantum communication and quantum computation. But there's also memory, and that we don't hear that much about quantum memory, and I hope we could hear more, because for the schemes that I've been presenting, it's super important to be able to store at the quantum level. So if you want to have your quantum money, not decohere. So if you want your investment to remain stable, you should be able to store it. And there's no classical description of this thing, otherwise it's not quantum money. So we really have to keep it at the quantum level. Same thing for the quantum programs or the ciphertexts. They have to maintain their coherence, otherwise their cryptographic properties disappear. And about the feasibility, I really don't know. I think the world records are milliseconds, so I think that's kind of something that could be improved.
Yeah, I guess because actually most of these schemes that you talked about, they only use BB84 states. That there is no entanglement at all. So I wonder if someone in the audience knows more about, what is the status of quantum memory, even for qubits that are not entangled. But I guess, yeah, while people think about that, I also had one question. So I think you mentioned the unclonable bit problem at some point. So basically, unclonable encryption, but just for a single bit.
Yeah.
And so I think I can sort of see that the monogamy of entanglement proof wouldn't go through. I think it's basically right because the two parties, Alice and Bob, can guess the bit. I think it's not like with probability half, but it would be like a half plus there's this 1 over square root of 2. I think that shows up in the monogamy of entanglement game.
Yeah.
Right. But I was wondering, are there any formal barriers? Like, do you think it's possible to prove that actually you can't do it?
Yeah, I'm just trying to get that slide so people can follow. No, I don't think that there are any barriers. I think it's limitations on our creativity. So this is this thing. So I think we need to find some scheme. Well, okay, actually think about it. There are schemes that come to mind, like using private simplification or hash functions or something, or maybe some more better encodings, but we don't have the proof techniques right now to deal with this simultaneous situation of both Bob and Charlie being simultaneous. They're both dishonest and they both need to predict the same message. It's a model that's super paranoid, and there's very limited work done in that area. It's even more paranoid than device independence, because in device independence, at least Bob trusts his classical processing, but here we don't even trust that.
I have a question, and maybe it has to do with where entanglement appears in this whole story. So, so one fixture for a lot of what you've considered here is the concept of unclonability, right? That's the basis for a lot of how you're conceiving of the games. But of course, when we think about the power of quantum computing, we also remark on how difficult it is to classically describe a very complex quantum state, that a quantum system can describe itself, but a classical computer has trouble capturing all of that. So, or that is this exponential size of Hilbert space. So where does that appear in these games in security and cryptography? Is it the same? Is it basically you have to go into entangled spaces in order to access that exponential capacity?
Yeah, maybe this is controversial, but I don't really buy the exponential capacity, because probability distributions also have an exponential number of outcomes. So, I don't see the direct link. Really, what we're exploiting is the complementarity of observables that you can try to measure in one basis or a complementary basis, but then if you measure in one basis, that destroys the information in the other basis. And this is something that you probably don't do in computing because you probably don't want to destroy information.
Mm-hmm. Mm-hmm.
And I have a related question, building on what Dan just asked. So all of the schemes that I'm aware of, and I think all of the schemes that were mentioned in the intro into your talk today, use EPR pairs as kind of the source of entanglement in these schemes. Are there any examples of using like any other kinds of entangled states that are useful in these cryptographic schemes?
Good question. Yeah, the EPR pairs come up in the proof. So if you like to prepare EPR pairs, you could do the EPR pair version, but probably you'd want to do the prepare and measure version instead, like the preparing Wiesner states. I guess the ones that I skipped over and didn't go into details, it's because they're more complicated and they don't have the Wiesner encoding. So the publicly verifiable quantum money uses hidden subspaces, which are probably at the bottom of it. If you dig pretty deep, they'll probably ended up encoded EPR pairs, like probably EPR pairs with a lot more structure. So probably large entangled states that have different, more interesting properties. Are you after a specific entangled state that you're wondering about?
I don't know. I guess something that like potentially comes to mind would be like trying to share information amongst more than two people, for example. So I don't know, then if you had like a GHZ state, which is just like n up spins plus n down spins, basically, instead of just like two correlated spins. Yeah, I mean, I don't really have much background in this field, so I don't know like what would be useful to think about. But yeah, like experimentalists can create other kinds of entangled states, like GHZ states. There's, I guess, another example is Dickey states, which are like completely symmetric superpositions of like n spins pointing up and n spins pointing down. Squeeze states. Yeah, so I don't know if, yeah.
The GHZ appears in some anonymous communication. So because of kind of the symmetry and the way the three parties can be treated in the GHZ, so that can be used for broadcasting anonymously. So that's kind of cool. Other than that, I don't know.
Okay.
I think Arthur has a question.
Hi, can you hear me? Yeah, thanks for the wonderful talk. Yeah, I was interested at the end, these unclonable proofs, and I was just sort of just spitballing ideas, but I wonder if anyone's ever thought of like unclonable strategies for non-local games. Maybe you could have a scenario where Alice and Bob know how to win the game with some high probability, but two other provers who don't actually possess a quantum strategy that can win the game with high probability, they intercept Alice and Bob's strategy, the entangled state, and what measurements they plan to perform. Then can both Alice and Bob and this malicious pair both simultaneously win the game with high probability? Is that I don't know, just spitballing ideas, but maybe that's along the same vein.
Yeah, I hadn't thought about that one, but that's a good one. Unclonable strategies. Yeah. So you'd have like families of games, and like maybe like they don't know which game they're going to be asked, but they're ready, and then another team arrives. You can wonder if they're able to share their power and their strategy or not with the other team.
Anyways, just putting it out there.
Yeah, this unclonable proof is intriguing because classically, usually people like to have like the opposite, which is like publicly verifiable proofs. right? Unclonable proof is the opposite.
Yeah, you have to watch Scott's after dinner talk. He says that you have the proof of the Riemann hypothesis in a vase. And you look it up at night, but you're the only one who can verify it. Kind of, yeah.
I guess I was kind of curious why one would want to make a proof unclonable. I feel like I don't really understand the idea very well.
You're not alone. So I think it's a challenge, and being able to define it, I think it's like a challenge to overcome. And once we've overcome that, maybe we'll understand more about unclonability. I think that's why the end benefit is the understanding. So it's what we do in complexity and computer science is come up with some cooked up scenario. It looks kind of weird, but usually it's a sandbox. So usually the reason why we just simplify the problem, it still looks complicated, but we still it's actually a simplification so that we can model it and then play with it as much as possible. And then once you understand the entire sandbox, then you can try to apply it further. So the analogy with zero knowledge proofs is that it's weird too. Zero knowledge is that anybody can verify this proof, but they should learn nothing about the proof by verifying it. And once we understood that, then you can actually spread that all through cryptography, non-interactive zero knowledge proofs, and all sorts of things. And you can convince somebody that your message is correct, even though they can't read the message. And that's super useful. So yeah, the why sometimes comes after the fact, but right now it's for the foundations.
I see. So what is an example of something that you could hope to learn by exploring the question of how to make a proof unclonable? Or you won't even really know that?
No, don't know that yet.
Okay. So understanding the question is also part of the question.
It's like there's unclonable questions. So, and can't reveal it to you.
Yeah, that's very interesting.
Now, similarly, there's also, quantum information is also used to make measurements of, let's say, environmental conditions. So there's probably scenarios where you want to confirm or hide the fact that somebody has made a measurement. I mean, I guess you're stating whether they've read the message, and but it's also whether they've sort of used the quantum resource to make some estimate of I don't know, something physical.
Okay, so from the point of view of the physical system, who are you trying to hide it from?
I guess from anybody else who might want to gain that information too. So you could imagine, I don't know. I may want to make a local estimate of some energy. So I'm given a starting state and it evolves in time, and then I measure it. But if that starting state is entangled with a starting state somewhere else, then, for example, I can't interpret the outcome of my measurement as pertaining to something about the local conditions without also gaining the knowledge from Alice or whatever about which starting state she had.
Mm-hmm.
So in other words, like measurements that have information content only when two specific partners share that information.
Oh, it sounds like secret sharing.
Maybe it's okay. Maybe it's secret sharing, but in terms of a function for that.
Yeah. Like locally, it doesn't, or even a code word. Like locally, if you only have a small portion of it, then it's actually maximally mixed. But if you have a larger portion of the system, then information is there.
Mm-hmm. So when people break these security protocols in practice, where are they breaking them? So, you know, when people break actual BB84 machines and whatever, what is their target of attack?
Oh, okay. So you must have heard of quantum hacking. And this has to do with, okay, so how's that possible, right? Because we have security proofs, and the problem is that the model that we're working in may not correspond to the physical system that's being used. So like this model is single qubit, single photon emissions, if you're like creating these Wiesner states, and that's not the case in the labs. So each time that there's a deviation between the formal model and the physical system, there's the potential for attacks and quantum hacking. So there was like, there's that at the source level, there's hacking at the detector level. So blinding the detector so that it's going to have some deterministic behavior based on the basis of the encoding, for instance.
So is there work on once those kinds of leakage channels are revealed? Is that also an area where people are actively looking for?
Yes. So there's a device-independent cryptography, which is it's supposed to be a general fix for any type of side attack, because instead of modeling, we no longer depend on the model of the physical system. We now model the quantum device as a box. You give it an input, it gives you an output, and you actually don't have any model on what it's actually doing. You don't have a model on the entanglement, on the measurement or whatnot. And then you're actually able, however, you need to introduce another assumption. So space-like separation. So actually, if the devices you buy two devices from a pirate, and then you separate them so that they're not able to signal, and then you challenge them, kind of cross-interrogate them, and then you can still become convinced that they're doing something cryptographically useful, like randomness expansion or quantum key distribution. That's device-independent quantum key distribution. Mm-hmm.
I have a question about like noise tolerant versions of these protocols, because it seems like in some sense, if you're trying to like share a message in this quantum protected way, you want to make sure that you're impervious to eavesdroppers, but you also might want to build in some tolerance to like decoherence in the channel that is unavoidable. So is there any way to kind of like balance these two requirements? Or are they like fundamentally?
This has been addressed in quantum key distribution, so we can look at there for inspiration, and like the certified deletion, since it's so close to quantum key distribution, it's able to take advantage of that already. So what happens in quantum key distribution is that exactly how you pointed out, you would want to, like if you go back to Andrea's example, they would want to, when they're doing the sampling, parameter estimation, you would want to accept even if there are a few errors. Fine, so let that be a parameter delta. You know, you're like, your accepted delta fraction is correct. But that gives a chance to the Eve to interfere or gain more information. So how do you squeeze out that delta? Well, you can still squeeze out the delta by tuning your privacy amplification. And the other thing is that, well, what if they end up with a key that's not the same? That's bad, right? Because there could be errors, and they might not know about that. So we actually use an error correcting code on top of the key. So you don't distribute a plain key. You distribute this random key. There might be some noise, but then there's some pretty standard error correcting mechanisms that, as long as the noise threshold is the noise rate is below a certain threshold, then you're almost guaranteed to have a corrected key that you share.
I see.
Yeah,
that makes sense.
But that's only known for QKD. I think all the other ones completely open, and like it hasn't really been looked at in detail, except yeah, I did cite the work on the quantum money, and they've made it noise tolerant.
Yes, that one I noticed. Mhm.
Yeah.
So what's the status of like national quantum initiatives in Canada? What's the
Interesting that you would ask. So
Stunning.
in the federal budget that came out, I think it maybe about 2 weeks ago, there was funding promised. Okay, I don't have the numbers in front of me. Either in the tens of millions or the hundreds of millions of dollars over a certain amount of years to establish a national quantum strategy. There's already a team of academics and industry and government that have been working on this for quite some years, but now it's in the government's budget. So, well, thank you. 360 million over 7 years. Thanks, Sebastian. So that's a good start, and yeah, now it's going to become a national priority.
And how is that slated to play out? Is there a division of labor among actors, or
they put in charge one of the ministries, but I don't know any more details of how that, how it goes to industry or government or academics or training, etc.
Mm-hmm. Mm-hmm. Well, good luck with that. Once word got out in the States that this was all coming, then everybody sort of got on their phones for the next 2 years, trying to talk with each other and figure it out and scheme and organize. And it was very time consuming. It still is.
Yeah. Well, turned out pretty good for your team, I guess.
Yeah. Knock on wood, we're doing pretty well. All right. Well, I might suggest we please stop recording now. Thanks so much, Anne. Let's see. How do I stop recording?